There is a number that most people have encountered, 384,400 kilometers. It is the average distance from the Earth to the Moon. It is large enough that no human being has ever driven it, or flown it, or walked it. Yet in the context of what this documentary will examine, it is effectively zero, and that is where the problem begins. Human perception was shaped by distances measured in meters and kilometers. The tools of intuition, the ability to judge how far something is, how large it is, and how long it would take to reach, were calibrated for a world of hills, rivers, and open plains. They do not extend to the cosmos, and they cannot. The first challenge of understanding the universe's largest structures is not finding them, but understanding what it means to measure anything at all at the scales where they exist. The cosmic distance ladder is the sequence of techniques astronomers use to measure progressively greater distances. Each rung is a method that works within a certain range and then fails, requiring a new approach at larger scales. The first rung is direct measurement using radar. A signal is bounced off a nearby planet, and its return is timed to calculate distance. This works within the solar system. The Sun is approximately 150 million kilometers from Earth. Neptune orbits at roughly 4.5 billion kilometers. These numbers already exceed anything a human lifetime of travel could cover, yet they still represent a tiny local neighborhood. Beyond the solar system, radar becomes useless. Signals would take years to return, and by the time they did, the target would already have moved. Instead, astronomers use parallax, the apparent shift in a star's position when observed from opposite ends of Earth's orbit. The star itself is not moving, the Earth is. That slight angular change reveals distance through geometry. The nearest star system, Alpha Centauri, lies approximately 4.24 light-years away. A light-year is the distance light travels in a single year, roughly 9.46 trillion kilometers. Parallax remains effective out to a few thousand light-years before the angular shifts become too small to measure reliably, even with modern instruments like the Gaia Space Telescope. Gaia has produced astrometric measurements for more than 1 billion sources, with reliable parallax data for hundreds of millions of stars. Further out, astronomers rely on what are known as standard candles, objects whose intrinsic brightness is already known, allowing distance to be calculated from how bright they appear in the sky. Cepheid variable stars pulsate with a period directly related to their luminosity. Measure the period, infer the luminosity, compare it with the observed brightness, and the distance follows naturally. It was this method that Edwin Hubble used during the 1920s to demonstrate that the Andromeda Galaxy lies far beyond the Milky Way, at approximately 2.537 million light-years away. It was not a nearby nebula. It was an entirely separate galaxy. At even greater distances, individual stars become impossible to resolve. The preferred standard candle then becomes the Type Ia supernova, a stellar explosion with a highly consistent peak luminosity. When a Type Ia supernova appears within a distant galaxy, its apparent brightness allows astronomers to calculate the galaxy's distance. This method extends measurements across billions of light-years. It was through observations of Type Ia supernovae that astronomers discovered in 1998 that the expansion of the universe is accelerating, driven by what is now called dark energy. Beyond even supernovae, astronomers rely on redshift. As the universe expands, light from distant galaxies is stretched toward longer and redder wavelengths. The amount of stretching, known as redshift, is proportional to both distance and recession velocity. Measure the redshift of a galaxy, apply the established relationship between redshift and distance, and its position in space can be determined. This technique, applied systematically across hundreds of thousands and eventually millions of galaxies, made it possible to map the three-dimensional distribution of matter across enormous regions of the universe. These maps, produced through decades of redshift surveys, form the foundation for everything that follows in this documentary. The structures examined here are not visible as single objects in telescope images. They are inferred from the statistical distribution of galaxies across immense volumes of space. A filament of the cosmic web does not appear as a filament when any individual section is photographed. It only emerges when the positions of tens of thousands of galaxies are plotted together and the larger pattern becomes visible. That is the central scientific challenge. Scale is not merely a descriptive problem. It is simultaneously a measurement problem, a statistical problem, and a conceptual problem. The tools developed to confront that challenge, including parallax, standard candles, redshift surveys, and gravitational lensing, each solved a limitation in the method that came before. Every step expanded the portion of the universe that could be explored systematically. The observable universe extends approximately 93 billion light-years in diameter. That number is not a wall. It is a horizon, defined by the age of the universe and by the finite speed of light. Everything examined in this documentary exists within that horizon. Some of the largest candidate structures occupy a significant fraction of its diameter. Understanding how those structures were identified, what they physically are, and what their existence reveals about the universe begins with something far smaller and far more familiar. A single galaxy. A galaxy is not simply a collection of stars. That description is accurate in the way that describing a city as a collection of buildings is accurate. It is technically true and practically misleading. A galaxy is a gravitationally bound system with structure, dynamics, and a mass budget that, once examined carefully, turns out to be dominated by something that emits no light at all. The Milky Way is the galaxy we know best, and it serves as the baseline unit for everything that follows. Its visible disk spans approximately 100,000 light-years across. Within that disk, somewhere between 200 and 400 billion stars are distributed across spiral arms, with a dense central bulge and a diffuse stellar halo surrounding the whole structure. The Sun sits roughly 26,000 light-years from the galactic center, in a relatively unremarkable stretch of one of those spiral arms. At the speed the solar system travels around the galactic center, approximately 230 kilometers per second, one full orbit takes about 225 million years. That rotation figure matters. It is where the first major discrepancy appears, and where the modern understanding of what a galaxy actually is begins to come apart from the older one. In a system where most of the mass is concentrated at the center, as the planets of the solar system orbit a central sun, the orbital velocity of objects decreases with distance from that center. Objects further out move more slowly. This relationship is described by Kepler's laws, and follows directly from Newtonian gravity. If the Milky Way followed the same logic, stars in the outer regions of the disk should orbit noticeably more slowly than those closer in, because most of the galaxy's mass would lie within their orbits. They do not. The rotational velocity of stars and gas in the outer disk stays roughly constant rather than falling off. In some galaxies, it even rises slightly with distance. This is called a flat rotation curve, and it was not what anyone expected to find. The astronomer Vera Rubin, working with her colleague Kent Ford at the Carnegie Institution of Washington, produced the most systematic and compelling evidence for this anomaly through the 1970s. Using a spectrograph sensitive enough to measure the Doppler shifts of light from stars and gas clouds at the edges of galaxies, Rubin and Ford measured the rotation curves of dozens of spiral galaxies. Galaxy after galaxy showed the same result. The outer regions were rotating far too fast to be explained by the visible mass alone. Visible matter alone could not account for the observed orbital velocities. And that discrepancy pointed directly towards something missing from the picture. The explanation that has since become standard is that each galaxy is embedded within a much larger halo of matter that does not emit, absorb, or reflect light in any wavelength that has yet been detected. This is dark matter. It interacts gravitationally, and its presence is inferred entirely through its gravitational effects on visible matter. The rotation curves that Rubin and Ford measured are not an anomaly in the data. They are a direct measurement of the gravitational influence of this invisible component. The dark matter halo of a galaxy like the Milky Way extends far beyond the visible disk. Current estimates place its outer boundary at somewhere between 500,000 and 1 million light-years from the galactic center, up to 10 times the diameter of the visible stellar disk. The total mass of the Milky Way, when the dark matter halo is included, is estimated at between 700 billion and 1.5 trillion solar masses, with significant uncertainty remaining. The stars, gas, and dust that make up everything visible in the galaxy account for only a fraction of that total. The dominant structural component, by mass, is the component no telescope has directly imaged. This interpretation is strongly supported by multiple independent lines of evidence. Gravitational lensing, the bending of light from background sources by the mass of a foreground galaxy, produces distortions whose magnitude reflects the total mass of the lensing object, not just its visible mass. In every case examined, the lensing mass exceeds the visible mass by a substantial factor consistent with a dark matter halo. The motions of satellite galaxies orbiting larger hosts, the behavior of gas at the edges of galactic disks, and the internal dynamics of galaxy clusters all point to the same conclusion. Visible matter traces a deeper structure that itself cannot be seen. What dark matter is made of remains one of the central open questions in physics. It is not ordinary atomic matter in a dark form, such as cold gas clouds or dim stars. The abundances of light elements produced in the early universe constrain how much ordinary matter could exist in total, and that constraint rules out ordinary matter as a sufficient explanation for the observed gravitational effects. The leading candidates are undiscovered subatomic particles, weakly interacting massive particles or similar species that were produced in the early universe and have been gravitationally clustering ever since. None has been directly detected in laboratory experiments, despite decades of dedicated searches. What is firmly established is the structural role dark matter plays. It does not merely accompany visible galaxies, it precedes them. In the early universe, before stars formed, dark matter began clumping under gravity, creating a network of filaments and overdensities. Ordinary matter, the gas that would eventually form stars, fell into those dark matter structures and condensed. The galaxies visible today formed inside dark matter halos, not the other way around. The architecture of the visible universe is, in this sense, a map of the underlying dark matter distribution. Every structure examined in the chapters ahead, from galaxy clusters to the vast filaments of the cosmic web, was shaped first by dark matter. The visible matter followed. Keeping that sequence in mind is essential to understanding why the universe is arranged the way it is. Galaxies are not uniformly distributed across space. They gather. The Milky Way belongs to a collection of more than 54 galaxies spanning roughly 10 million light-years, a structure known as the local group. Andromeda is its other major member. The rest are smaller galaxies, dwarf systems for the most part, bound to one or the other of the two large spirals by gravity. The local group is not a loose association. Its members are gravitationally committed to one another. In roughly 4.5 billion years, the Milky Way and Andromeda will merge. The local group is, by the standards of what exists elsewhere in the universe, a modest structure. There are galaxy clusters that contain not dozens of galaxies but thousands, packed into a volume that, while enormous by any everyday measure, is compact relative to the scales the documentary will reach in later chapters. Understanding what distinguishes a genuine cluster from a chance alignment of galaxies, and what the interior of a cluster actually contains, requires looking beyond the visible galaxies themselves. The Coma cluster is one of the most thoroughly studied rich clusters in the sky. It lies approximately 320 million light-years from Earth in the constellation Coma Berenices. Within a region roughly 20 million light-years across, it contains over 1,000 galaxies, most of them elliptical or lenticular in form. Its total mass is estimated at around 700 trillion solar masses. By any measure, it is an extraordinary concentration of matter, but the galaxies themselves account for only a fraction of that mass. The distinction between a cluster and a random grouping of galaxies comes down to gravitational binding. A gravitationally bound system is one whose members do not have enough kinetic energy to escape the collective gravitational pull of the whole. The galaxies in a bound cluster are orbiting within a shared gravitational well, and they will continue to do so for the remaining lifetime of the universe. They are not passing through, they are not moving apart. They remain gravitationally bound. Confirming that a cluster is genuinely bound requires measuring the velocities of its member galaxies. If those velocities are below the escape velocity set by the total mass of the system, the cluster is bound. When astronomers first applied this test to the Coma cluster in the 1930s, the Swiss astronomer Fritz Zwicky found a problem. The galaxies were moving far too fast relative to the visible mass of the cluster. Based on the luminous matter alone, the cluster should have dispersed long ago. The velocities implied a total mass far greater than the stars and gas could account for. Zwicky proposed that the cluster contained large amounts of unseen mass, which he called dunkel materia, dark matter. This was decades before Vera Rubin's rotation curve work applied the same logic to individual galaxies. The cluster dynamics had already pointed in the same direction. The resolution to Zwicky's discrepancy came in part from X-ray astronomy. When space-based observatories began surveying the sky in X-ray wavelengths, galaxy clusters appeared as some of the brightest sources in the X-ray sky. The reason is a component of clusters that optical telescopes cannot detect, the intra-cluster medium. Between the galaxies in a cluster, filling the space that appears empty in visible light images, is a vast quantity of superheated plasma. In the Coma cluster and similar rich systems, this gas has been heated to temperatures between 10 million and 100 million Kelvin. At those temperatures, the plasma emits radiation not in visible light, but in X-rays. The Chandra X-ray Observatory and the European XMM Newton Observatory have mapped this emission in clusters across the sky, revealing the spatial distribution, temperature, and density of the intracluster medium in considerable detail. What those observations showed was significant. The intracluster medium accounts for more baryonic mass than all the stars in all the cluster's galaxies combined. In a rich cluster, the hot gas typically constitutes around 12 to 15% of the total mass. The stars in the galaxies account for only about 1 to 2%. The remainder, roughly 85% of the total mass, is dark matter, inferred from the gravitational behavior of both the gas and the galaxies. The X-ray observations also revealed the physical processes operating within clusters. The plasma is not uniformly distributed. It is denser toward the center and more diffuse at the outskirts. In some clusters, the central gas is dense enough to cool relatively quickly, drawing more gas inward in what is called a cooling flow, though subsequent observations showed that active galactic nuclei at cluster centers inject energy that partially suppresses this cooling. Clusters are not static. They are dynamic systems, still accreting matter from their surroundings, occasionally merging with other clusters in collisions that represent the most energetic gravitational collision events known in the universe since the Big Bang. The Bullet cluster, observed at a distance of roughly 3.7 billion light-years, provides one of the most direct pieces of evidence for dark matter's role in cluster structure. It is the aftermath of a collision between two galaxy clusters. The hot gas of the two clusters, detectable in X-rays, was slowed by electromagnetic interactions during the collision and lagged behind. The galaxies and, as gravitational lensing maps confirmed, the bulk of the mass passed through largely unimpeded. The mass distribution and the gas distribution are now spatially offset. Dark matter, which interacts only gravitationally, behaved as expected. It kept moving with the galaxies while the gas was dragged back. The lensing map and the X-ray map tell two different stories about where the mass is, and together they confirm that most of it is not in the gas. Galaxy clusters are the largest structures in the universe that are genuinely gravitationally stable. They will persist. The structures above them in scale, the superclusters and filaments examined in the chapters ahead, are not bound in the same way. They are transient configurations, shaped by gravity but not held by it. That distinction is not a technicality. It is the boundary between what the universe will preserve and what it will eventually pull apart. Step back far enough from a galaxy cluster, and it becomes apparent that clusters themselves are not isolated. They occur in proximity to other clusters, connected by bridges of galaxies and gas, grouped into larger concentrations that span hundreds of millions of light-years. These aggregations are called superclusters. They represent the next tier in the hierarchy of cosmic structure. But the step up from clusters to superclusters is not simply a step in scale. It is a step across a fundamental physical boundary. Galaxy clusters are bound. Their members will not escape. Superclusters are different in a way that matters enormously for how they should be understood. They are not held together by gravity. They are being pulled apart by the expansion of the universe, even as their internal regions remain locally concentrated. A supercluster is not an object in the way a cluster is an object. It is a configuration, a pattern in the distribution of matter that exists at a particular moment in cosmic history and will not persist indefinitely. Establishing this required a new way of mapping structure. Redshift surveys give the positions of galaxies in 3 dimensions, but position alone does not reveal whether those galaxies are gravitationally associated or merely adjacent. What reveals gravitational association is motion. Galaxies in a region dominated by a large mass concentration will move toward that concentration, deviating from the smooth expansion of the universe. These deviations are called peculiar velocities, and measuring them requires separating the velocity due to cosmic expansion from the velocity due to local gravity. The technique works as follows. A galaxy's total recession velocity, measured from its redshift, is a combination of the expansion of space and its own motion through space relative to the local matter distribution. If the distance to the galaxy is known independently, through a method such as the Tully-Fisher relation, which links a spiral galaxy's rotation speed to its intrinsic luminosity, then the expected expansion velocity at that distance can be calculated and subtracted. What remains is the peculiar velocity, the galaxy's motion driven by gravity alone. Map enough peculiar velocities across a large volume of space, and the underlying mass distribution begins to emerge, not from where galaxies are, but from how they are moving. This is the method that Brent Tully and his collaborators at the University of Hawaii applied, with results published in 2014. Using a database of peculiar velocities for thousands of galaxies, they mapped the flow of matter across an enormous region of the nearby universe. What they found was that the Milky Way, along with hundreds of thousands of other galaxies spread across a region previously thought to contain several distinct superclusters, all lie within a single vast basin of gravitational attraction. They defined this basin by tracing the flows. Every galaxy whose peculiar velocity directed it inward toward the same central attractor was counted as part of the same supercluster. Where the flows diverged outward toward a different attractor, the boundary of the supercluster was drawn. The result was Laniakea, a name drawn from the Hawaiian meaning of immeasurable heaven. It spans approximately 520 million light-years and contains the mass equivalent of roughly 100 million billion solar masses, encompassing around 100,000 individual galaxies by the original 2014 mapping, including the Milky Way, the Virgo cluster, and numerous other clusters and groups. It is the largest coherent structure to which the Milky Way can be said to belong in any physically meaningful sense. But Laniakea is not bound. This is the critical point. The mass concentration that defines it is not sufficient to overcome the expansion of the universe across its full extent. Galaxies near its edges are already being carried away by cosmic expansion faster than the gravitational pull of the supercluster can draw them back. Over billions of years, Laniakea will not collapse into a single structure. It will disperse. The flows that currently define its boundaries will be overwhelmed by expansion, and the coherence of the whole will dissolve. This means that the definition of a supercluster had to be reconsidered. Prior to the 2014 work, superclusters were typically defined by galaxy density. Regions where galaxies were more concentrated than average, identified from redshift surveys by looking for overdensities above a certain threshold. That definition did not distinguish between regions that were gravitationally associated and regions that merely appeared proximate. Tully and collaborators proposed a new definition based on dynamics rather than density. A supercluster is the region within which all peculiar velocities flow toward a common attractor. This is a physically grounded definition, one that connects the identification of a structure to the gravitational physics that produces it. Even under this new definition, Laniakea is not a stable object. It is the largest scale at which local gravity currently dominates over cosmic expansion in this part of the universe. It is a watershed in the hydrological sense, the boundary where water divides between different drainage basins. On one side of Laniakea's boundary, matter flows inward. On the other side, it flows toward a different attractor entirely. That boundary is not sharp in practice, and it will shift over time as expansion continues. The attractor toward which much of Laniakea flows is not located within Laniakea itself. It lies beyond its edge, in a region of space that will become the focus of the chapter that follows. The peculiar velocities that define Laniakea do not terminate at its boundaries. They point outward towards something more massive still, something that was pulling at the Milky Way and its neighbors long before astronomers had the tools to identify what it was. In the 1970s, astronomers studying the peculiar velocities of galaxies in the local universe noticed something that resisted easy explanation. The Milky Way was not moving through space in a direction that matched any obvious nearby mass concentration. It was moving, along with hundreds of thousands of surrounding galaxies across a region spanning several 100 million light-years, toward a point in the southern sky in the direction of the constellation Centaurus. The velocity of that motion was approximately 600 kilometers per second. Nothing visible in that direction accounted for a gravitational pull of that magnitude. The inference came before the identification. Astronomers knew something large had to be there, because the motion of so many galaxies, all converging on the same region, left no other physically coherent explanation. A flow of that scale and that consistency does not arise from noise or statistical fluctuation. It requires a genuine mass concentration, one substantial enough to exert a gravitational influence across hundreds of millions of light-years. The source was given a name before it was seen: the Great Attractor. The reason it could not be seen was geographical, in a cosmic sense. The Great Attractor lies in a direction that falls almost exactly behind the densest part of the Milky Way's own disk. Looking toward Centaurus from Earth means looking through thousands of light years of the galaxy's own stars, gas clouds, and dust lanes. This region of the sky, where the plane of the Milky Way obscures background objects, is called the zone of avoidance. It is not a sharp edge, but a broad band across the sky where optical observations become progressively more difficult and eventually impossible. Galaxies that lie behind the galactic plane are hidden not because they are intrinsically faint, but because the Milky Way itself is in the way. For optical telescopes, the zone of avoidance is a genuine blind spot. Dust absorbs and scatters visible light so effectively that even relatively nearby galaxies, at distances of tens of millions of light years, can be completely invisible in optical surveys if they happen to lie behind the densest parts of the galactic plane. The Great Attractor sat almost perfectly within this blind spot, which is why it took so long to characterize despite being close enough to exert a measurable influence on the Milky Way's motion. The partial solution came from wavelengths that dust does not block as effectively. Radio waves and infrared radiation pass through the galactic plane with far less absorption than visible light. Beginning in the 1980s and accelerating through the 1990s, surveys in these wavelengths began to reveal galaxies and galaxy clusters behind the zone of avoidance that optical surveys had missed entirely. The most significant find in the direction of the Great Attractor was a rich galaxy cluster in the constellation Norma, designated Abell 3627 and commonly called the Norma Cluster. It lies approximately 220 million light-years from Earth and is one of the most massive clusters in the nearby universe, with a total mass estimated in the range of 1 quadrillion solar masses. The Norma Cluster became the leading candidate for the core of the Great Attractor. Its mass and position were broadly consistent with the direction and rough distance implied by the peculiar velocity data. For a time, it seemed that the mystery had been substantially resolved. The Great Attractor was a massive cluster hidden behind the galactic plane, now partially revealed by infrared and radio observations. But the peculiar velocity data did not fully settle. When astronomers refined their measurements and extended their surveys to greater distances, it became clear that the Norma Cluster, while genuinely massive, was not massive enough on its own to account for the full amplitude of the observed flow. The galaxies of the local universe were not merely falling toward the Norma Cluster. They were falling toward something further away and considerably larger. That larger structure is the Shapley supercluster, located approximately 650 million light-years from Earth in the same broad region of sky. It was identified by the British astronomer Harold Shapley in 1930 as an unusual concentration of galaxies, though its full extent and significance were not established until redshift. Surveys in the 1980s and 1990s mapped its membership in detail. The Shapley supercluster is one of the most massive known concentrations of matter in the nearby universe, containing dozens of galaxy clusters and groups, and carrying a total mass in the range of tens of millions of billions of solar masses. Its gravitational influence extends across an enormous volume of space, and its direction from Earth aligns closely with the observed flow toward the Great Attractor. Current models suggest that the Shapley supercluster is responsible for a substantial fraction of the peculiar velocity of the local group, perhaps around 50% of the observed 600 kilometers per second. The Norma cluster contributes a portion of the remainder as a more local concentration along the same line of sight. Together, these two structures account for much of the motion, but the accounting is not complete. Surveys conducted in the 2010s and into the 2020s have continued to find mass concentrations behind the zone of avoidance and at distances beyond Shapley that may be contributing to the observed flow. A structure catalogued as the Vela supercluster, identified in 2017 at a distance of roughly 800 million light-years, appears to exert a measurable gravitational influence on the local flow field. Whether the combination of Shapley, Vela, and the Norma cluster fully explains the motion of the local group, remains an open question. The peculiar velocity field in this region of the universe is complex, and the mass concentrations that drive it have not all been identified with certainty. What the Great Attractor episode illustrates clearly is how much of the universe's structure was hidden not by distance but by the geometry of our own position within a galaxy. The zone of avoidance is being slowly opened by advances in radio, infrared, and X-ray astronomy, and each new survey reveals more of what lies behind it. The picture of what is pulling the Milky Way through space continues to grow more detailed and more complicated with each successive observation. In 1986, Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics published a map of galaxy positions covering a thin slice of the sky extending out to roughly 200 million light-years. It was one of the first outputs of the CFA redshift survey, and what it showed was not what most astronomers had expected to find. The galaxies were not scattered randomly across the volume. They were arranged along thin, curved sheets and filaments, surrounding large regions that contained almost nothing at all. The structure resembled the surface of a foam or the interior of a sponge. Galaxies traced the walls. The interiors were empty. That image established a new way of thinking about the large-scale universe. The question was no longer simply where galaxies are, but why they are arranged this way, and what occupies the spaces between them. The answer had already been partially worked out on theoretical grounds, and it came from dark matter. In the early universe, matter was distributed almost uniformly, but not perfectly so. Tiny fluctuations in density, imprinted during a period of rapid expansion called inflation and detectable today in the cosmic microwave background, meant that some regions were marginally denser than others. Gravity amplified those differences over time. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter to their surroundings, becoming emptier. The process is not random. It has a preferred geometry determined by the initial conditions and the behavior of dark matter under gravity. Dark matter, because it interacts only gravitationally and not through any electromagnetic process, began clustering earlier and more efficiently than ordinary matter. It collapsed first along sheets, then along the intersections of those sheets to form filaments, and then at the intersections of filaments to form nodes. Ordinary matter, the gas that would later form stars and galaxies, fell into the potential wells that dark matter had already established. The result is the structure visible in galaxy surveys. A cosmic web of filaments and nodes with vast empty regions in between. The filaments themselves are not uniform threads. They are elongated concentrations of galaxies, gas, and dark matter, typically spanning tens to hundreds of millions of light-years in length and several million light-years in width. They channel matter from the surrounding regions toward the cluster nodes at their intersections, feeding those nodes with galaxies and gas over cosmic time. The nodes are where the richest galaxy clusters form and grow, sitting at the convergence points of multiple filaments like junctions in a network. Between the filaments and sheets lie the voids. These are regions of space that are not truly empty, but are dramatically underdense compared to the cosmic average. They contain some galaxies, typically smaller and more isolated than those found in filaments or clusters, but far fewer than statistical chance alone would place there. Voids evacuate over time. As gravity pulls matter toward the surrounding filaments and walls, the interiors become progressively emptier. They also expand. Because voids contain less mass than average, the cosmic expansion inside them is slightly faster than the global average, and voids grow larger over time, while their interiors grow increasingly sparse. The Bootes void is one of the largest and most thoroughly studied voids in the nearby universe. It was discovered in 1981 by Robert Kirshner and collaborators, who were conducting a survey of galaxy redshifts in the constellation Bootes, and found a region roughly 250 to 330 million light-years across depending on the survey and boundary definition, containing far fewer galaxies than any statistical model of random distribution would predict. In a volume that should have contained hundreds of galaxies based on average cosmic density, only a handful were found. Subsequent surveys have identified around 60 galaxies within its boundaries, but relative to expectations, it is one of the most dramatic underdensities known. The precision with which the cosmic web was predicted by simulation before it was fully mapped by observation is one of the more striking convergences in modern cosmology. N-body simulations, which model the gravitational interactions of enormous numbers of dark matter particles over cosmic time, began producing web-like large-scale structures in the 1980s. The Millennium simulation, run in 2005 using over 10 billion simulated particles, produced a dark matter distribution whose filamentary structure matched the observed galaxy distribution in considerable detail, down to the characteristic scales of voids, filaments, and cluster nodes. The match is not perfect, and discrepancies at small scales continue to be studied, but the broad agreement between simulation and observation is robust. Starting from the initial conditions inferred from the cosmic microwave background, applying only the known laws of gravity and the established properties of dark matter, and running the simulation forward for 13.8 billion years, produces a universe whose large-scale structure closely resembles the one mapped by redshift surveys. That agreement is not a coincidence. It is confirmation that the physical model is capturing the dominant processes correctly. Subsequent surveys extended and refined the picture established by the CFA redshift survey. The 2-degree field galaxy redshift survey, completed in the early 2000s, mapped the positions of over 220,000 galaxies. The Sloan Digital Sky Survey extended that to nearly 1 million galaxies across a much larger volume. The ongoing Dark Energy Spectroscopic Instrument Survey, which began full operations in 2021, is on course to map tens of millions of galaxies out to distances of billions of light-years, providing a 3-dimensional picture of the cosmic web with a resolution and completeness that earlier surveys could not approach. Each successive survey has confirmed and elaborated the same basic architecture: a network of filaments and sheets, nodes of concentrated mass at their intersections, and vast voids occupying the majority of cosmic volume. That network is not merely a description of where galaxies happen to be. It is the fossil record of how structure grew from the earliest moments of the universe, and it encodes, in its statistical properties, information about the physics of those earliest moments that can be extracted and measured with the right tools. The cosmic web is not simply a description of where galaxies are found, it is a record, encoded in the statistical properties of the web, in the precise way that galaxies cluster at particular scales and avoid one another at others, is information about conditions that existed long before any galaxy formed. That record is described mathematically through the matter-power spectrum, a measure of how much clustering exists at each spatial scale across the universe. A scale with a high value is one where galaxies are significantly more likely to be found near other galaxies separated by that distance. A scale with a low value is one where the distribution is closer to uniform. The shape of that curve was not arbitrary. It was set by quantum mechanical fluctuations in the very early universe, during the inflationary period that preceded the hot, dense phase. Those fluctuations were stretched to cosmological scales, and their statistical distribution, nearly but not exactly scale invariant, matches the measured power spectrum with considerable precision. At the largest scales, the web is ultimately a record of quantum events that occurred in the first fractions of a second after the Big Bang. Superimposed on this broad shape is a feature that carries an extraordinarily precise and useful signal. In the early universe, before the first atoms formed, ordinary matter existed as a hot plasma of protons, electrons, and photons. The photons and ionized gas were tightly coupled, behaving as a single fluid. That fluid supported pressure waves, acoustic oscillations, that propagated outward from each primordial density fluctuation at slightly more than half the speed of light, carrying both photons and ordinary matter outward together. This continued for approximately 380,000 years, until the universe cooled enough for protons and electrons to combine into neutral hydrogen. At that moment, called recombination, the photons decoupled from the matter and streamed freely across space. Those photons are now the cosmic microwave background, but the pressure waves stopped. The ordinary matter, no longer coupled to the photons, could no longer be pushed outward. The waves froze in place, leaving shells of compressed ordinary matter at a fixed distance from each original density fluctuation, approximately 490 million light-years in comoving terms. This scale is called the sound horizon. That frozen shell is detectable today. Regions separated by this characteristic distance are slightly more likely to both contain galaxies, because both the original overdensity and the shell became preferential sites for subsequent galaxy formation. The signal, called the baryon acoustic oscillation, appears as a subtle but measurable excess in the probability of finding pairs of galaxies separated by roughly 490 to 500 million light-years. It was first detected statistically in 2005 by Daniel Eisenstein and collaborators using data from the Sloan Digital Sky Survey. Because the physical size of the sound horizon can be calculated precisely from the known properties of the early universe, it functions as a standard ruler. Measure its apparent angular size at a known redshift, compare it to the predicted physical size, and the ratio gives a precise measurement of distance. Do this at multiple redshifts, and the result is a detailed record of how the expansion rate of the universe has changed over time, which is precisely what dark energy governs. The Dark Energy Spectroscopic Instrument, operating at the Kitt Peak National Observatory in Arizona, is currently the most powerful instrument dedicated to this measurement. Early data releases have already produced some of the tightest constraints on dark energy yet obtained, and the full survey will extend those measurements across a much larger volume. The cosmic web, which began as a description of large-scale structure, has become one of the primary tools through which the universe's composition and history are measured. Its statistical properties encode the initial conditions set by inflation, the physics of the early plasma, and the subsequent influence of dark energy across billions of years. That dual role, subject of study and instrument of measurement simultaneously, becomes increasingly apparent as the documentary turns to the largest individual features identified within it. In 2003, J. Richard Gott and Mario Jurek, working with data from the Sloan Digital Sky Survey, identified a concentration of galaxies that appeared to form a continuous structure approximately 1.37 billion light-years in length. They called it the Sloan Great Wall. At the time of its identification, it was the largest structure yet reported in the observable universe, surpassing the CFA Great Wall identified by Geller and Huchra in 1989. The Sloan Great Wall sits at a distance of approximately 1 billion light-years from Earth. The identification raised a question that has not been resolved in the 2 decades since, and that question is more fundamental than it might initially appear. It is not simply a question about this particular structure. It is a question about what the word structure means when applied to objects at these scales. The tools used to identify large-scale structures in galaxy surveys are statistical. The most foundational is the two-point correlation function, which measures the excess probability, above random expectation, of finding two galaxies separated by a given distance. For identifying specific large structures, rather than characterizing the whole distribution, astronomers use a different approach. The Friends of Friends algorithm links galaxies into groups by connecting any two galaxies separated by less than a chosen linking length. Vary that length and different structures emerge. Short lengths identify only the densest compact groups. Longer lengths connect more galaxies into larger associations. The critical choice is a linking length that identifies physically meaningful structures without simply connecting everything into an undifferentiated whole. The Sloan Great Wall was identified using a linking length calibrated to the mean galaxy separation in the survey. At that linking length, the galaxies it encompasses appear connected into a single continuous structure. But whether the lower density bridges between its denser regions represent genuine physical connections, or merely the result of a linking length generous enough to span physically significant gaps, is a matter of interpretation. The structure is not gravitationally bound. The Sloan Great Wall spans far too large a volume for gravity to hold it together against cosmic expansion. It is an overdensity, a region where the galaxy distribution is higher than the cosmic average, but it does not meet the physical criterion of gravitational coherence that defines a cluster. The more difficult question is whether it is a single overdensity or several overdensities that appear connected due to the choice of linking length or the distorting effects of redshift space. Redshift space is not identical to real space. The peculiar velocities of galaxies distort their apparent positions along the line of sight. Dense clusters produce elongated smears in redshift maps, the finger of God effect. At larger scales, coherent infall compresses structures along the line of sight. These distortions do not create fictitious structures from nothing, but they can make separate structures appear more connected than they are. Independent analyses of the Sloan Great Wall have reached different conclusions, with some studies fragmenting it into distinct components, and others finding the continuous structure of the original identification, using the same data but different statistical assumptions. What would settle the question is a combination of things current surveys only partially provide. A complete peculiar velocity map of the region to reveal whether the constituent parts share coherent mass flows, and a denser galaxy sampling in the lower density bridges to clarify whether those connections are genuine filaments or artifacts of the chosen linking length. The Sloan Great Wall sits at a scale where the definition of structure becomes genuinely ambiguous, not because the observations are poor, but because gravitational binding, the clean physical criterion that defines clusters, is no longer applicable. At scales where binding is irrelevant, a different kind of definition is needed, and that definition does not yet exist in a form that commands universal agreement. The structures examined in the chapters ahead push further into this ambiguity, and in some cases press against the limits of what cosmological theory predicts should exist at all. To map structure at distances of billions of light-years, individual galaxies become increasingly difficult to detect. Quasars offer a partial solution. These are the extremely luminous cores of active galaxies, powered by matter accreting onto supermassive black holes. A quasar can outshine its entire host galaxy by a factor of hundreds and be detected and have its redshift measured at distances where the surrounding stars are entirely invisible. That makes quasars useful tracers of the large-scale distribution of matter in the distant universe. Quasars are not uniformly distributed. Because the galaxy mergers and gas infall that trigger quasar activity are more common in overdense environments, quasars preferentially appear where the underlying dark matter density is higher. A concentration of quasars at similar redshifts can therefore indicate an underlying concentration of matter, a dark matter filament or node hosting elevated levels of quasar activity. Roger Clowes and his collaborators at the University of Central Lancashire identified a collection of 73 quasars in data from the Sloan Digital Sky Survey, all lying at redshifts corresponding to distances of roughly 9 to 11 billion light-years from Earth. Using a friends of friends algorithm with a linking length calibrated to the characteristic scale of previously identified large quasar groups, They found that these 73 quasars formed a single connected association spanning approximately 4 billion light-years. The result was published in 2013 and designated the Huge Large Quasar Group. The scale of that claim was significant in a specific and quantifiable way. The cosmological principle, which holds that the universe is homogeneous and isotropic when viewed at sufficiently large scales, implies that coherent structures should not exceed roughly 1.2 billion light-years as an upper bound. A structure of 4 billion light-years would exceed that bound by a factor of more than 3, representing a direct challenge to the cosmological principle as currently formulated. The methodological objections focused on two specific points. First, the linking length. The Friends of Friends algorithm is sensitive to this parameter. A longer linking length connects more points into larger groups. Critics argued the linking length used was not independently justified for this specific quasar sample, and that a shorter length would fragment the huge LQG into several smaller and less remarkable associations. Second, the statistical baseline. To assess whether the grouping is genuinely unusual, it must be compared to what a random distribution of quasars with the same overall density and clustering properties would produce. Subsequent analyses argued that the comparison samples used did not adequately account for the intermediate scale clustering already known to be present in quasar distributions, which would cause the algorithm to produce larger connected groups even in the absence of any physical superstructure. A detailed reanalysis by Nadather in 2013, using simulated quasar catalogues with realistic clustering properties, concluded that the Huge Large Quasar Group was not statistically significant once known quasar clustering was properly accounted for. Clowes and collaborators disputed these conclusions, arguing that the comparison statistics introduced their own assumptions that were no more neutral than those in the original work. The exchange illustrated a recurring difficulty at the frontier of large-scale structure. Different defensible methodological choices can lead to substantially different conclusions from the same underlying data. What is not in dispute is the observational fact that 73 quasars at similar redshifts are found in spatial proximity as described. The disagreement is whether that proximity constitutes a coherent physical structure or an artifact of the method applied to a clustered population in a large survey volume. The Huge Large Quasar Group also highlights a fundamental limitation of quasars as structure tracers. They are sparse. The 73 quasars are distributed across a volume that, if filled with the galaxy density typical of a moderately rich environment, would contain millions of galaxies. Inferring the detailed geometry of any underlying dark matter structure from so few traces spread across 4 billion light-years requires assumptions about quasar clustering that introduce substantial uncertainty into any conclusion about the physical nature of the association. Gamma-ray bursts are the most energetic, explosive events in the observable universe. They occur when massive stars collapse at the end of their lives, or when compact objects such as neutron stars merge, releasing in seconds an energy output that, if emitted equally in all directions, would match what the Sun emits across its entire 10 billion year lifetime. That energy is concentrated into a narrow beam of gamma radiation which, when oriented toward Earth, is detectable across cosmological distances far greater than those accessible to ordinary galaxy surveys. The most distant gamma-ray bursts ever recorded originate from sources more than 13 billion light-years away. Because gamma-ray bursts require massive, short-lived stars, and those stars form preferentially where gas is dense, the rate of gamma-ray bursts is expected to be higher in regions of elevated matter density. That link between burst rate and environment makes them potential tracers of large-scale structure at very high redshifts, in regions too distant for conventional galaxy surveys to map in any statistical depth. It was this reasoning that led Istvan Horvath and his collaborators to examine the directional distribution of gamma-ray bursts in the known catalogue. Between 2013 and 2015, they published analyses focusing on bursts with measured redshifts corresponding to distances of roughly 9 to 11 billion light-years. Within that range, they identified a region spanning the constellations Hercules and Corona Borealis, where gamma-ray bursts appeared to occur at a higher rate than in surrounding regions. If taken at face value as a physical structure, the overdensity would span approximately 10 billion light-years, by a considerable margin the largest candidate structure ever reported, approaching roughly 1/10 of the diameter of the observable universe. The detection method has properties that make this claim exceptionally difficult to evaluate. Gamma-ray bursts are not a uniformly sampled population. The SWIFT satellite, which provided a substantial portion of the redshift measured bursts used in the analysis, does not observe all parts of the sky with equal sensitivity at all times. Some regions accumulate more observing time than others, meaning an apparent clustering of bursts in a particular direction might reflect observational bias rather than a genuine physical concentration of matter. Correcting for these biases requires detailed modeling of the instrument's exposure history, which is technically difficult and introduces its own uncertainties. The sample size compounds the problem. Only a subset of the available bursts fell in the specific redshift range used to identify the structure. Drawing conclusions about structure on scales of 10 billion light-years from a sample of several tens of events requires the statistical signal to be extraordinarily robust. Subsequent analyses have reached different conclusions. Some independent examinations found evidence consistent with an overdensity in the reported region. Others, applying different statistical tests or using more complete catalogues with better characterized selection effects, found the significance reduced to a level consistent with a random fluctuation. The disagreement mirrors what was seen with the huge large quasar group. The same data can support different conclusions depending on which statistical framework is applied and how observational biases are modeled. What would be required to resolve the question is substantially more data. A gamma-ray burst catalogue, an order of magnitude larger than currently exists, with well-characterized selection effects and uniform sky coverage. Future high-energy satellite missions may eventually provide catalogues of this size, but they do not yet exist. The claim therefore remains in genuine scientific suspension, not confirmed and not refuted. If the structure is real, the implications are specific and serious. A physically coherent structure spanning 10 billion light-years would represent a density fluctuation on a scale highly difficult to reconcile with standard cosmological expectations. The matter-power spectrum falls steeply at large scales, and the probability of a genuine coherent overdensity of that extent arising from the initial conditions established by inflation is extremely small under standard assumptions. A confirmed detection would require either a significant revision to inflationary theory, a modification to the growth rate of structure, or the conclusion that the cosmological principle fails at scales previously assumed to be safely within the homogeneous regime. That last possibility connects this structure to a broader pattern of findings that will be examined in the chapter that follows. The cosmological principle is not an observational finding. It is an assumption, one built into the mathematical foundation of modern cosmology and supported by a substantial body of evidence, but an assumption nonetheless. It states that the universe, when viewed at sufficiently large scales, is homogeneous and isotropic. Homogeneous means that its properties are the same everywhere. Isotropic means that it looks the same in all directions. Together, these properties mean that the laws of cosmology derived from observations made in one region should apply equally everywhere. The scale above which homogeneity is expected to hold is derived from the matter-power spectrum and from measurements of the cosmic microwave background. On scales above roughly 300 million light-years, and conservatively above perhaps 1.2 billion light-years, The universe should be statistically uniform. Individual structures can exist below that scale without violating homogeneity, in the same way that individual trees do not violate the uniformity of a forest viewed from altitude. What the cosmological principle does not permit are coherent physical structures or statistically significant density variations that persist well above that threshold. The findings examined in recent chapters each represent, to varying degrees, a potential tension with that expectation. None has been confirmed to the standard that would require a revision of the standard model, but the pattern is worth examining as a whole. The giant arc, reported in 2021 by Alexia Lopez and collaborators at the University of Central Lancashire, adds a further data point. It was identified not through galaxy positions or quasar clustering, but through the distribution of magnesium absorption systems in the spectra of background quasars. When light from a distant quasar passes through an intervening cloud of gas, the magnesium in that gas leaves a characteristic absorption feature in the spectrum. By cataloguing the redshifts of these absorption features across a large number of quasar sightlines, Lopez and collaborators mapped the distribution of intervening gas at a distance of approximately 9.2 billion light-years. What they found was a curved arc spanning approximately 3.3 billion light-years, with a spatial coherence the authors argued was statistically significant at roughly the 3.3 sigma level. Because it uses a different physical probe, intervening gas rather than quasar positions or gamma-ray bursts, its existence as a reported anomaly is at least partially independent of the methodological debates surrounding those other structures. The cosmic microwave background contributes a qualitatively different category of evidence. Its temperature fluctuations are consistent with standard model predictions at small and intermediate angular scales. But at the largest angular scales, several anomalies have been identified. An unexpectedly low amplitude of fluctuations at the largest angles, an alignment between the quadrupole and octopole moments unlikely under standard assumptions, and a hemispherical asymmetry in which one half of the sky shows slightly larger fluctuations than the other. Each has been studied extensively. None has been universally accepted as either systematic error or new physics. The theoretical responses fall into a few categories, none of which has yet produced testable predictions confirmed by independent data. Models that modify the physics of inflation can produce departures from scale invariance at specific scales, but they introduce additional parameters without yet constraining them observationally. Models that treat dark energy as a dynamical field rather than a fixed cosmological constant could in principle produce larger density contrasts than the standard model expects, but whether they resolve the large-scale anomalies specifically has not been established. The most conservative interpretation is that the anomalies are real statistical fluctuations within the standard model, unlikely but not impossible, and that finding several simultaneously is less surprising than it appears, because the same large-scale modes of the density field may contribute to multiple observed anomalies at once. What is not available is a theoretical proposal that accounts for the full set of anomalies in a unified and predictive way. The cosmological principle remains the working assumption of the field. The evidence examined here is sufficient to motivate serious investigation of alternatives. It is not yet sufficient to require them. The observable universe has a boundary, but that boundary is not a wall, not an edge of space, and not a region where matter stops. It is a horizon, and understanding what a horizon means in a cosmological context requires separating two things that intuition tends to conflate: the age of the universe and the size of what we can see. The universe is approximately 13.8 billion years old. A naive calculation might suggest the observable universe extends 13.8 billion light-years in every direction, since that is the distance light could have traveled since the Big Bang. That figure is wrong. And understanding why is central to understanding what the observable horizon actually means. Space itself has been expanding throughout the history of the universe. A photon emitted 13.8 billion years ago was traveling through space that was simultaneously stretching beneath it. The source of that photon has been carried away by cosmic expansion during the entire journey. By the time the photon arrives, the source is far more distant than 13.8 billion light-years. The current distance to the most remote objects whose light is reaching us now, accounting for the full expansion history, is approximately 46 billion light-years. The observable universe is therefore a sphere roughly 93 billion light-years in diameter, centered on any observer anywhere in the universe, since each observer has their own horizon centered on their own position. The oldest light detectable is the cosmic microwave background, emitted at recombination approximately 380,000 years after the Big Bang. That surface of last scattering sits at a look-back time of approximately 13.8 billion years, but at a current comoving distance of roughly 46 billion light-years. The microwave background is not the edge of the universe, it is the edge of what is directly visible, a curtain of opacity beyond which earlier cosmic history cannot be accessed through electromagnetic radiation. Gravitational waves and neutrinos from earlier epochs could in principle carry information from before recombination, but detecting them at cosmological distances remains beyond current capability. The distinction between look-back time and comoving distance is fundamental to interpreting the distances of the largest structures discussed in this documentary. When a structure is described as lying 9 or 10 billion light-years from Earth, that figure refers to its look-back time. The light now arriving was emitted that long ago. The current physical distance to that structure is considerably greater. The Hercules Corona Borealis Great Wall, if it exists as described, spans a region whose comoving extent of roughly 10 billion light-years represents a substantial fraction of the observable radius of 46 billion light-years. That fraction is itself a source of difficulty. Identifying an anomalous density requires comparing the observed density to an expected background. If the structure in question is large enough to influence the measurement of that background within the survey volume, the comparison becomes circular. This is a practical limit on identifying and confirming structures at the largest scales, independent of the specific detection methods used. The universe beyond the observable horizon is not accessible to any measurement. The physics that produces the horizon is well understood. What lies beyond is genuinely unknown and, in principle, unknowable through direct observation. The universe could be finite, with a specific geometry and topology. It could be infinite. Current observations cannot distinguish between these possibilities. Within the observable universe, the structures examined in this documentary occupy a hierarchy that runs from galaxy clusters at tens of millions of light-years to candidate superstructures at billions. The Laniakea supercluster, at 520 million light-years, represents less than 2% of the observable diameter. The Sloan Great Wall at 1.37 billion light-years, the Giant Arc at 3.3 billion, and the huge large quasar group at an estimated 4 billion each represent progressively larger fractions. The Hercules Corona Borealis Great Wall, at the claimed 10 billion light-years, approaches nearly a quarter of the observable diameter. Each step up in scale brings a corresponding reduction in the statistical tools available to assess whether a structure is real, because larger structures are rarer, sampled by fewer traces, and more difficult to disentangle from the background against which they must be measured. The observable horizon is not just the limit of what can be seen, it is the limit within which the scientific tools developed to understand cosmic structure can operate, and some of the largest candidate structures are already pressing against that limit in ways that constrain what can be said about them with confidence. The distribution of matter across the observable universe is not a random arrangement. It is a record, and reading it requires understanding which features encode which physical processes and at what precision those processes can be reconstructed from what is observed today. The starting point is the cosmic microwave background. Its temperature fluctuations, measured across the full sky by the Planck satellite, constitute the initial conditions from which all subsequent structure grew. The amplitude of those fluctuations, their statistical distribution across angular scales, and the precise ratios of the acoustic peaks together constrain the composition of the universe at the time of recombination. These constraints are tight. The fraction of the universe's total energy content contributed by ordinary baryonic matter is approximately 5%. Dark matter contributes roughly 27%. The remainder, approximately 68%, is dark energy. These figures come not from a single measurement, but from the simultaneous fitting of a model to multiple independent observational constraints. The large-scale structure observed today is the evolved state of those initial conditions. Dark matter began clustering from the moment of matter-radiation equality, approximately 50,000 years after the Big Bang, building the web of filaments and nodes into which ordinary matter subsequently fell. The statistical properties of the resulting galaxy distribution, the matter power spectrum, and the baryon acoustic oscillation signal carry the imprint of both the initial conditions and the subsequent growth history. They are sensitive to the total amount of dark matter, to the expansion history driven by dark energy, and to the sum of neutrino masses. Large-scale structure is therefore not merely a map of where things are. It is a precision instrument for measuring the fundamental parameters of the universe. The next generation of surveys is designed to exploit this with substantially greater statistical power than has previously been available. The Euclid mission, launched in 2023, is conducting a wide field survey of galaxy shapes and positions across more than a third of the sky, out to redshifts of approximately 2, using a galaxy sample of approximately 1.5 billion objects. The dark energy spectroscopic instrument takes a complementary approach. Where Euclid measures galaxy shapes across a broad area, DESI measures galaxy redshifts spectroscopically, producing precise three-dimensional positions for tens of millions of galaxies and quasars. The Vera Rubin Observatory, in Chile, will image the southern sky repeatedly over 10 years, contributing primarily through weak gravitational lensing and galaxy cluster identification. Together, these three instruments offer cross-checks between different measurement methods, shapes, positions, and temporal depth that substantially reduce the systematic uncertainties affecting any single approach. These surveys will also have bearing on the anomalous structures discussed in earlier chapters. The huge large quasar group and the Hercules Corona Borealis Great Wall were identified from sparse samples in limited survey volumes. The new surveys will not directly observe these specific structures, but the statistical tools developed and validated on their vastly more detailed maps will sharpen the ability to judge whether high redshift claims are consistent with the standard model or genuinely anomalous. Some questions that appear open today are, in principle, answerable with foreseeable data. Whether the baryon acoustic oscillation scale remains consistent across different redshifts, whether the growth rate of structure matches the predictions of general relativity, and whether the statistical properties of the cosmic web at intermediate scales are fully consistent with the standard model, are all questions the next decade of surveys is positioned to address definitively. Others are answerable in principle, but not with instruments that currently exist. Confirming or refuting the largest candidate structures at distances of 9 to 11 billion light-years would require a spectroscopic survey of gamma-ray bursts or similar high redshift tracers, an order of magnitude larger than any existing catalogue, with well-characterized selection effects and uniform sky coverage. That instrument does not yet exist, and some questions may not be answerable at all. What lies beyond the observable horizon, whether the cosmological principle holds in regions whose light has not yet reached us, and what the universe looked like before the inflationary epoch that set its initial conditions, are questions that the observable universe, by its nature as a bounded region of space and time, may never be able to resolve. The largest structures accessible to observation sit near the edge of what can be measured. They were shaped by processes that preceded any direct observation. What they record about those processes is real and detectable and still being read. Whether the record is complete is another question entirely.